is this is a restart of Billion Bits. We actually haven't done a Billion Bits in about a year and a half. We were just talking. So the idea for Billion Bits is to kind of bring the wider technical community together. So in Kansas City, traditionally there have been kind of the big tent events, whether it's KC Developer Conference and quite a few others, Midwest I/O, California has a good conference, and so that happens kind of on an annual basis. And then there's a bunch of user group conferences, and so front-end design, DevOps, like all kinds of different things. We try to be kind of the happy medium between the two, although we're probably going to be not monthly like we were before, but at least every, on a semi-regular basis, actually try to bring the group together. And so we talk about a lot of different topics, and the idea is that we kind of bring, as I said, a different set of disciplines. So normally we kind of do this, who's a developer in the room? Okay. How about kind of DevOps, backend? Yeah, I guess I'm going to hold my hand up for a few of these as well. Network engineering, security. Okay. There's a whole bunch. So we're probably going to be doing mostly over here. So I don't know. It would be awesome to like integrate you guys a little bit more. But yeah. So and then let's see, embedded engineers. Okay. Assembler, anybody? Yeah, one guy. Okay, yeah, so the idea is, and apparently we've kind of succeeded today, we've brought a nice combination of folks together to talk about kind of some of these interesting and interconnected issues. And really we try to break the conversation down into a series of different topics. So evolution of the network, how's the network changing, and what's that enabling? Software frameworks and approaches, so a bunch of different stacks, a bunch of different things. Proliferation of computing and algorithms, and this time we're kind of focused on that topic because as kind of algorithms develop and computing becomes more and more ubiquitous, a lot of interesting things happen, like computer vision, natural language processing. We'll do awesome talks on those topics. We added pretty late in the game kind of an embedded computing IoT component because a lot of things change as you lose memory and processing power and things get disconnected, weird things happen, right? And then applications. Ideally, at some point, we will have an application where all of the other topics are combined in this application, and maybe general AI, I don't know. But we haven't had one where it's, a connected robotic device using CV over some kind of mesh network yet. But we're looking, so if you guys have any ideas and folks that are doing some interesting things across all these areas, we're all here. So it'd be an awesome thing to kind of get together. So yeah, today's topic is, and we kind of sensationalize the title a little bit, the rise of the machines, but kind of in the world of proliferating algorithms and computing, there's a lot of interesting things that are coming together to enable a bunch of applications. And so we're gonna have two talks, one focused on kind of computer vision, augmented reality, and another one on kind of machine learning for natural language. And that seems like, natural language processing, but there's a big gap between what we're able to do today and, kind of the people sitting in this room. And we'll have kind of speaker dig into that a little bit. The format is always kind of an intro, and this is a little longer intro since we haven't done this in a while. Then kind of an open mic events going on around the community. We try to be super inclusive. I think John's got an announcement, but anybody can have 30, 45 seconds to introduce whatever's inside your, events, topics, that kind of thing. Probably do that for about 5 minutes just to stay on time, and then jump into a talk. So I'm Billy Tabak, by the way. I'm one of the organizers. John Wagner is another organizer. This does not happen without a lot of support. CTOPO is very gracious to make the logistics and space easy. And so thanks a lot to John Christopher and kind of the rest of the CTOPO gang. KC Digital Drive supports us and a lot of the outreach and that kind of stuff. And all of these come together because somebody is interested in a topic and they know something that's going on. So if any of you want to organize one and think of a topic, that kind of thing, come talk to me, come talk to John. We'd love to have you kind of join and think about, what else can we do? Because if we get a little bit more support there, we can start to talk about moving into a monthly thing. if that's interesting. So I guess announcements. John, you have one?
Just real quickly, folks. Hi, I'm Jonathan Wagner. I'm the founder of a tech company in town called Big Bang. We're a platform, cloud platform for Internet of Things. But I'm here today actually representing KC Digital Drive, because I also do work for them. They are supporting 1 billion bits. And we have an event coming up on the 30th that's called the Gigabit Workday. And I would really encourage you folks to try to drop by. I believe it's going to be in the Google Fiber space. I should probably really know that before I can. Yeah, okay, I'm getting a thumbs up video. Okay, it's going to be the Google Fiber space. There's going to be a lunchtime session, but you can kind of come and go all day. You don't need to sort of stick around the whole time. But the focus is on gigabit applications and creating gigabit applications. There's like a whole huge spiel I can go into, but the 30-second version is that Kansas City is one of about a dozen cities that's working with an organization called US Ignite to help create ecosystems for gigabit applications, because we've got the fiber, right? We're like one of the original folks with the fiber. So we have the connectivity in the city, but we need infrastructure to make interesting gigabit applications possible. We're building something in the city along with about a dozen other cities called Digital Town Square, which makes sure that all the traffic for your applications, like all the communications, stays local. There's no reason for your video stream to come from this table, bounce all the way out to California, and then come all the way back to see you, right? We don't need the latency or the mess of that. We want to have the best, fastest, lowest latency communications. It's critical for certain types of applications. We're going to be talking about machine vision, and there's a real interesting argument for doing machine vision in the cloud by streaming that information back from your camera into the cloud, as long as the cloud is really, really close, right? So that's what the Digital Town Square can do. So anyway, we'd love to have you come out to the Gigabit Workday on the 30th at the Google Fiber space. Just come up and talk to me afterwards. I can give you some more core details, but please check that out. And that's all I got.
Yeah, who else? Anyone else? Nope. All right.
Not to put you on the spot, any exciting meetups, events, anything like that going on around town? What's the next thing you guys are excited about? Other than the K game, what's the next technical thing you guys are excited about? Although, I don't know, the NAA tournament had, and I'm sure you'll talk a little bit about kind of what the issues with doing some of the sports recognition is. Yeah. Sports and tech are becoming an interesting thing. I think I'll not steal your thunder on that, but yeah.
I'm not thinking of the presentation right now, but I'll talk about it.
Cool. All right. Anybody? All right. We will do suggestions next time so I can read them off the list. All right. Cool. Thanks for coming. I'm going to turn it over to Joel Teply, and he'll talk to us about augmented reality and computer vision. And first, we're going to plug that.
There you go. All right. Thanks. My name is Joel Teply, and we started a company about 6 years ago called Cambrian. And it was based around initially just an application where you touch the wall, change the paint color. Pretty simple app, wasn't much to it. You could probably think of it as it's kind of like a green screen replacing the color. Relatively trivial concept, but after noticing how popular it was, first day I was kind of surprised it had 12,000 downloads. I realized we should probably turn this into a little bit more of a business. So from there, we just started, turning it into an SDK, licensing it out to other companies, and then moving on to other forms of augmented reality, particularly around video in the home improvement sector. And there's not too much competition for us right now. So we're one of the few that is actually focused on this area, but we have the same exact concerns as someone developing a game like Pokemon. And so we have to do some low-level computer vision, and then of course machine learning, which I'll talk about in a little bit here, and a lot of other mathematics. So what I wanted to try to do is get everyone interested in first computer vision, and then really start to dive into deep learning. We are relatively new to deep learning. We just use some pretty basic classifiers and things like that in previous years, but lately, in order to solve some of the harder problems, which I'll get into, there's no other solution other than the deep models. I think, and now that the phones are really fast, since we do augmented reality on the iPhone and Android devices, they're fully capable of learning some of these deep models as long as they're pretty simple. So I'll start with this quote here from the economist, and it says, "The simplest computer can run rings around the brightest person when it comes to wading through complicated mathematical equations. At the same time, the most powerful computers have in the past struggled with things that people find trivial, such as recognizing faces, encoding speech, and identifying objects and images." That's a little bit of a demotivator there, but when you start out with a framework such as OpenCV or Caffe, which we're using for the deep, it does start to solve these problems. Maybe not with the same level of accuracy that you're expecting, but it's making a leap. And all of you have probably seen the self-driving cars and certainly the augmented reality that's around here. But So at the top here is kind of the traditional machine learning flow. And usually you just kind of start with an image, for instance. This could be audio as well, it wouldn't matter. You pull the features out, and then from that, you just run it through, for instance, a classifier. So finding an eye was something we worked on and I verified. And then another project, which I'll probably talk about, finding a basketball goal. And then it's relatively unreliable. A classifier only should be a little bit better than 50% accuracy at each stage. So a cascade classifier basically just moves through selecting, is it this or this or this or this, and then eventually it gets pretty decent accuracy. But a deep learning algorithm is a lot more kind of brute force approach to the problem. And instead of designing the feature extractors, maybe the additional algorithms that are in between input and features, it basically, in its simplest form, is going to give it a set of labels at the end, and then a set of inputs. And so long as you set up everything, it's just let it run through several iterations and let it learn. There's some really good examples on Caffe and then TensorFlow, et cetera, where they'll show you how to use it to identify numbers or various animals. Scifar is what that's for. It's not that bad. I mean, I talk about just reading this up, but these examples get you started with anything. If you can identify an animal in a 40 by 40 image, you can just as easily, in our case, for instance, identify a sink or a washing machine or a floor or a person. So it's not overly complicated. Now, that said, obviously we have some very sophisticated machine learning algorithms that are out there where people are pioneering a lot of different models. You've seen perhaps the Google deconvolution neural networks that are improving, taking a horrible image, for instance, and improving the accuracy through super resolution type effects. So it can be done, and then of course, self-driving cars, which are quite capable of making decisions. So this is kind of an example of what machine learning would be doing. At the input layer, it's going to kind of break it apart into features. So you don't really set this up. You can control weights manually, but in general, these are the types of decisions that it's going to make after the hidden layer, which is up the front. Is there an eye at the top left? If so, then it goes on that pad. Is there an eye at the top right, et cetera, et cetera? Is that here at the top? And then I've kind of broken down in more detail what that's going on in terms of the top, the eye decision, for instance, other eyebrows, et cetera. But it's really just statistical calculations and then weights applied to that. It's not actually like obviously asking these questions. But given the labels at the end and given the input at the beginning, it is able to come up with these types of decision making. And at the end, maybe identify it as a face or a cat or a car, et cetera.
Okay, and here is actually, if you were to take an image and look at each layer, you can see what is actually broken as apart into. And you can observe the output of each of these images, and it kind of breaks it apart into basic components, and then from these basic components, it slowly arrives at a result of a phenotype base, for instance. This is basically what's going on in the human brain. We might be more like the first example, which would be feature detectors. In our eye, we have some very low level optical effects, like the equivalent of a board, for instance, where it's just seeing edges that are kind of pronouncing edges stronger than they used to be. And then from that, we move into some intermediates that are very similar to a deep model, which is sitting it across to for various components, and there's some 3D processing in there as well. And then at the end, we end up making a decision. So we use Cafe for what we're doing, and it's an open framework. It's pure C++, which is why I like it. Since we run everything on the mobile phone, we have to run everything in real time, and hopefully somewhere between 30 and 60 frames per second. So in order to do that, we need something that's very speedy. I like it particularly because it's not, it can be scripted in Python if you'd like to, but you don't have to. You can start with basically a JSON syntax and develop your models. It's very, very lightweight. It also works with OpenCV very easily. And they have a lot of demos out there, and they also have a large user base. It's having burden. So this is just kind of an example of the script on the right-hand side. As you can see, it just looks like JSON. And from what you download, what you install, they have plenty of tutorials on it. It's going to only take you a few hours probably to get set up and running. And you're classifying numbers, or you're classifying animals, or whatever to your heart's content. And you can also very easily share weights across the two layers. And I'll show you a Siamese network in a second, which takes advantage of that. So this is what we used for our first example, called Siamese because it's identical on both sides. But it's efficient at the way that it shares basically features across or weights across between the two sides, and it's very good for comparison. So we're using this for a flood fill algorithm, and a flood fill algorithm basically just takes one patch and compares it to another and decides whether or not to proceed. And so we trained a network on floor patches and just trained it how to detect edges. It's a glorified edge detector or segmenter. I'll show you an example of that. So I think I'm going backwards. So here's an example of the training data. So the green areas are our success or ones. So they would be one labeled 1, and the red areas are 0. You could also label the other sections as a number label. And then we gave it several hundred images to run off of, and we were able to take advantage of our own programs to generate some of these images. I don't like some of the work that takes place in deep learning, which is very labor intensive, but there are some open sets that you can get access to, including in segmentation. It will save you a lot of time, and most of them are free. So given our timeline, we had to do a lot of the labeling ourselves, but we will also be taking advantage of some of this. This here is an example of it running. This is just in our office at Village Square, and the center, I don't know if you can see the center point down in, where there's not a circle inside a square. That was where the start of the flood fill occurred, and it was able to determine using these segments of comparing two together whether or not you should proceed or not. And you can see it kind of messed up in the corner there, and that's very typical of machine learning or any image processing. And after this, typically the strategy is to just go in and do geometric refinements, maybe run it multiple times, compare the outputs. If someone's holding a phone up, I probably Each frame is going to be very similar to the last one, so we can determine that this is noise over in the corner. There's other strategies such as Kalman filtering and things like that that will work for you. Here's an example of the rendering. This is a repeating tile of hardwood applied. It's done a pretty good job going around the carpet and everything else like that. It's rendering a 3D model. The reflections and everything like that are traditional machine vision type effects. We've got a blur in there. We have some thresholding, some other. They're very basic operations that are just math based, so algebra pretty much. Again, very similar. This is running at a trade show. It runs in real time, so it's basically a threaded architecture running C++, and each, along with tracking, which is good or bad depending on kind of the lighting conditions. And then hopefully, if we do a good job, we've done a good architecture, we can render anything. We can use the same system to render like a piece of furniture. But I find segmentation definitely a lot harder with just with placing a model in augmented reality. You're not concerned about segmentation. Segmentation can be very rough, especially considering lighting. So I'm going through this, basically this color wheel, and then there's a 3D rotate. And we've messed up a little bit. You can see it went up on the wall. So the segmenter went a little too far, especially here. Although this is possibly a little bit of like tracking error. And I can talk about that a little bit too. But in general with computer vision, you have some very basic principles. So the first might be optical flow, motion tracking. The others are feature finders. And these feature finders are very, very primitive, often because they have to run very quickly. A good example would be surf. That's designed to run often in the GPU. And it's just, if you look at the algorithms, it's just very simple. It's comparing, starting from one location, coming up with a set of weights or a set of numbers to represent the surrounding proximity of that. And there are plenty of papers on what works best, and some are free and some are patented, like surf. But they all actually are pretty great. This is a really good paper that I think people should read from Google. It's called the CAT paper. If you just look up Google the CAT paper, it'll talk about how this operates. But basically, what they did that was a little bit unique here is they, instead of manually picking out the labels at the end, I'll say that's a cat or that's a person, they just let it on its own. So it's completely unsupervised learning. And they noticed that on the bottom right-hand corner, they had a 70% relative improvement over the highest overall result. And so this is most effective for even self-driving cars, because we get into situations where there's road cones or the roads are eroded, it's snowing, it's raining, the traffic light's broken. It would be very hard for you to do that with a purely algorithmic approach or a completely machine vision approach. So with some of this unsupervised learning, it will accomplish it better, but it's also a little scary at the same time, because you don't know what kind of decision making it's going to make, or it could identify a bunch of, you've probably seen the photos of like absolute noise, and it says it tricks it into thinking that it's a cat or a person or whatever. So it's out of control. It's a little bit scary. If you're talking about robots taking over, it's probably going to be this. But its accuracy is so much better, and I think this is really the future of machine learning. And I think the next photo, you probably saw that this week. So this they managed to trick a self-driving car, and this is where an algorithm would fail. I mean, we just said, hey, you can never cross the white line and you're going to get stuck. And so you can see that if you watch the video, the car is just like nudging forward and getting a little bit confused, and it can't get out of it. And that could be good. I mean, because it's not going to just randomly drive off at a pedestrian or something like that. But at the same time, it's really limited. And a human would, even a toddler, my son would have no problem with this. I think he'd probably take off driving and I'd be running after him. But we have frustration as humans. We have a lot of other things. And computers, we don't know exactly what that is. That's probably just complete chaos or randomness. Who knows? Maybe but here is an example of a car. I think this has the most promise. This example is better, and so this will show you a car that probably would not I think it's really important to show when these things mess up. Oh, these are courageous people. And that right there is very, very impressive. Got it. Probably a little bit promotional for NVIDIA, but they're doing really great things. So one of the ways, especially with augmented reality, that we are able to speed things up is using the GPU for computation. So we use GPU. Basically, we'll do something very, very low level, like in your vision system, where we do like a Bohr filter or a Sobel filter, which are more like bench finders. We'll do that in the GPU. It's a basic operation. It's again just basic math. Convolution again is just looking at proximity and applying weights and adding everything together. Very, very simple operations. Those are very good to do on the GPU. Most of the time in your code, you're probably not even using the GPU. Even in our work, where we do a lot of 3D rendering, we still have a lot of additional resources that are available there. And so NVIDIA is doing a great job, probably trying to promote more than anything their own GPUs and CUDA, which is excellent. And it runs. I mean, when you see how fast, especially in training, which is very, very frustrating, it can take a week, it can take even longer than that. When you run it through a GPU, it might take 100, maybe 100 times faster, 10 times faster. So it's saving yourself a lot of time. What we do, we have NVIDIA machine, and then we also use the Amazon cloud. There's tutorials on how to set up a cafe training system on the Amazon cloud. If anyone's interested, I can certainly send them to that. It's inexpensive. Certainly turn it off when you're not using it. The GPU instances can rack up some cache, but while we're running, it's pretty basic. And for the work that we did, it would only take maybe 30 minutes to an hour to train. We're of course running these on mobile phones, so they're not nearly as deep as some of the other models we'll see out there. But it does work pretty well. Our deep model that I was showing you is running It's running for each of those squares. So it's running hundreds per probably a second or half a second on an iPhone. And so it can run quickly. And if you have a well-designed architecture, you can run some of these things off on their own threads and then use a combination of some of the feature tracking to then adjust its results back to the overall solution and hopefully not drift like some of the work that I had. Anyway, thank you for having me here. And if anyone would like to get started, I just really would love for them to get into machine learning. Certainly, if you've not already checked it out, look at OpenCV. It's incredibly well written. It's incredibly efficient. Their deep module requires a little bit of extra configuration. I don't know why it's not enabled for mobile devices right now, but it's pretty trivial to get running. But first of all, I think that everyone should not be intimidated by any of this. We've thrown a lot of what we worked on together in weeks. We had a trade show and we only had about 2 weeks to work on the deep learning model. And it worked out fairly well, and I think anyone here is going to be fully capable of doing it. And just get started with some kind of project that you're really interested in, something you want to solve. Certainly, identifying things would just be downloading the sidebar example of the image for animal recognition or image recognition. There's also ImageNet examples. There's plenty of other stuff out there, but it's really fun and it's completely the future. And I enjoyed it so far.
Awesome. We like to be super conversational, so we built in about 10 or 15 minutes for Q&A. We get the other microphone on just so folks, if they look at the live stream later, can hear your questions.
You can have mine.
Well, yeah, then we can hear you.
Okay.
Hello. Who's that? All right. Anybody have a question? Awesome. There you go, Mike.
Before you introduce machine learning into your application, was it primarily just OpenCV, or was it just you came with your own algorithm to detect the agency on that?
Yeah, so the place I started, I love Photoshop. I've been involved in art forever. I just like that. I don't even know how I came up with this concept, but started out with basic algebra. I just started trying thresholding using various image formats or color formats. Sorry. So I would go into HSV or HLV, either way, but hue, saturation value, and try, based on the area that I touched, could I compare that to everything else? Is there enough of a difference? I just ran a blunt fill. And so I started with really basic concepts, and I tried that with lab color, etc. And then it wasn't really sufficient, especially for lighting conditions. So I started moving into more and more sophisticated algorithms, but this was all through OpenCV. And then when we tried working this on the same thing for walls and floors, it failed miserably, painted maybe 3 or 4 pixels. So the first thing I tried classifiers, and then I tried just an artificial neural network, which did a little better than that. Then I tried both at the same time, and it did pretty well. It ran really quickly, but it was still not really getting the accuracy that we wanted, and nothing is ever getting the accuracy we wanted. So then I just started searching for deep models, and I tried Torch, I tried TensorFlow, and then lastly I tried Caffe. I should have gone there first. And I saw that, the learning curve on it was not much. With Torch, there were a bunch of Lua interpreters, and getting that to work on all these mobile phones was really annoying. We have an SDK, So for us to give someone a very large binary is also a big problem. So the Lua stuff just, I don't know, it just felt kind of like a bad idea to have an interpretation of another language when it didn't need to. And with C++ and Cafe, it just was very easy right out of the box. Their demos worked right away. My patience wasn't really tested like the other forms. And so I just started trying that. First thing I tried was basically I took the sidebar example, which is for, I think they're 40 by 40 images of various animals. I tried switching out the animals and putting in floor, putting in cactus, etc. I labeled all of my images. And that did okay, but it wasn't quite sufficient. And so I thought, okay, well, I'm already running a flood fill algorithm, so why don't I just rewrite the flood fill algorithm to run a deep model for every 2 segments. And I tried that with much better results. It was very important to output the error rates, output the success rates. And I would just run it on a series of 300 images and compare it to the last attempt and just keep doing that. Slow at first, so what I did is I took the Cafe model and started messing with the stride of the convolution. And so it moves a little faster as it moves across, as it swings across, and it had very negligible impact on the actual results. So maybe we lost 3% accuracy, but it was 5 times more efficient. So we went with that, and that unfortunately was probably more deadline based than anything. But we plan on working some deconvolutional neural networks when we're ever able to go back into this, but and really focusing on the segmentation problem. There's a lot of examples out there. Project Tango is doing some of this, but yeah, it started out with really primitive machine vision, moved into the GPU a little bit, and then we started really hitting the deep stuff. Anybody else? Thanks.
So one thing that's really interesting to me, I think it relates to the examples are related to like self-driving vehicles, but honestly, it's anything. It's that when you write, if you write your own classifier, or if you're writing something that's based on mathematics, then you kind of have a deterministic behavior, right? Like if I put this model and I put a picture of the Terminator up and I can recognize it, it'll be like, it's Terminator. But when you're using machine vision, you always get, your results always fuzzy, right? You always kind of like, it's probably Terminator, or it's kind of Terminator. And so I was curious how do you feel about the idea that you have these systems that have this like indeterminate behavior, and you also don't really know, like you don't really understand how they work. Like, because you've trained them, you've given them this example, you've given them all these images, and you say this is a Terminator, this is all these different things, but then at the end of the day, you don't know whether at any given moment it might give you a crazy answer occasionally. And I guess the example I'm thinking of is that I was explaining this, like the same thing I was showing to Google, that draw something.
Oh yeah.
Which is like super fun. Everyone gets that. Like it's the second you see it, right? It's like
draw a shoe.
Yeah, it's like draw a picture of a shoe. And the first thing is like it's an ostrich. It's a turkey. Oh no, it's a shoe. And you get like a real great feel for how those kind of things work. But sometimes it's when you see the exemplars, you will realize, okay, maybe I just didn't know how to draw a shoe. Like, I don't know, like everyone else draws a shoe totally different from my head. Or you're just like, why did it come up with this result? I don't know. So I guess what I'm asking is that how do you see that like working in sort of real world applications? Because if you got your self-driving car and like it sees something crazy and then it acts in some sort of bizarre way, you really don't. It's hard to test for that, I guess. Except for just sort of like pounding millions of miles and checking for when it veers off the road and crashes and burns. I saw the self-driving person from Nissan. They were here, and they showed us an example of how localized driving conditions are different and how people behave differently. And they showed us like this super crazy intersection in Iran, which was like Frogger. Like there's cars going 35 miles an hour, and it was just like like ladies with strollers, just like walking right out in front of cars, and it's like,
Oh yeah, our employee Sarah is from Iran, and that's actually right here.
yeah, I mean, it's great, it's crazy, it's just like, this is not sane, but people were not getting run over. But, it's like, I don't think they're driving a car that you trained in, like, can't see.
Yeah, I think we just have to have, I think we just have to be comfortable with failure. I mean, I've done a lot, I've failed a lot. I think we just have to compare, like, Tesla just got in trouble for a car that caused an accident, but the National Highway Safety Board or whatever, they determined that it was safer. So, or that it wasn't as dangerous as people were maybe saying. It's scary that a robot can kill a person, absolutely. There's a situation where it's like you hit 3 pedestrians or 1. That's or none, I guess. But we're talking about killer robots, so I think I'd like to have some low-level algorithms involved. I don't want it to be so restrictive that it's getting a car stuck in a circle, but I'd like to at least break it apart into some of the more primitive ways. I mean, we've seen this in our own evolution, that the eye and brain break things down into very basic components. Well, let's maybe give that to the machine learning algorithms. And even on the other end, maybe make a little bit of additional decisions that are maybe based on geometry or run 2 competing against each other. I think there's a lot of flexibility in terms of what you want to try, but I feel like the right solution is not just a big black box that just solves the problem. And maybe I'm wrong, but it just kind of, after being a developer for so long, it seems like that we need to have a little bit of control over it.
Great.
Did I even answer your question?
Yeah, I did. The only other thing that came up, you just mentioned the thing about the eyes and how we break things down. And I just think it's really fascinating to see how that machine vision suffers from some of the same foibles that we do. Like, people are trying to see faces, and so we'll see faces and things that, like the man in the moon, right? You're like, yeah. And, like the Google Inception thing is like the perfect example of the images where it's like suddenly there's birds and frogs. If you run it through the neural network in that time, all of a sudden, like, there's things appearing that were not in the source context.
And that's what I think. I think that the moment that your machine learning algorithm is fooled by optical illusion, you've probably succeeded.
Probably, yeah.
And so I think we're always looking at, like right now, all the processors and all the coding is based around absolute precision, where they're glorified calculators. I mean, if you go back to the processor, it has not changed like it should have. GPUs are not much of a step, they're just massive parallelization. I think that the way that these problems are going to be solved is with a little bit more flexibility. And so what we use, one of the things I first worked on, and this is now like 2 years ago, is called our binocular cues. So we're working with a mobile phone. And in psychology, they're in the vision system in the brain. There are things like vanishing points can be a good example, or what you see in optical illusions with lines cascading, etc., or the Mobius strip, etc. You can train algorithms to work off of that. So one of the first things I did for wall detection is I just looked for a vanishing point or a series of parallel lines, and I ran them through something called ransack, which is incredibly effective in computer vision. And it's basically, it takes a hypothesis, is this a square? Is this a plane? For instance, I was trying to find a wall. And then it tests it. And so it tests it based on a score. You write the part of the algorithm, you write the whole thing, but you write the part of the algorithm that determines that score. And so what I was doing is just looking at all the lines I found in the image. Are they converging, diverging, etc., and then giving it a score based on that. And it was actually incredibly effective at that problem. And I think you take that output again and move that through a deep learning network, and it would be even more effective. I was working on a program very recently to do sports tracking, to find the basketball court, to find its orientation. First place I started was just basic feature finding, and then pose estimations called. That's stock out of OpenCV, but that doesn't always work out. I mean, if there's not a logo on the court, or just you for some reason there's some blur, which is what we're certainly dealing with non-experts, then it starts to fall apart. So then I started trying like some more primitive things. And I think sometimes just being creative is the #1 way to solve a lot of these problems. I don't think there's any right solution. It's really in its infancy. The self-driving cars were like losing these dark events. You've seen the robots falling down, but like within a matter of years, like we're already using them. So, but just I think in this field in particular, to be very creative is the #1 beneficial trait. And then, so anything you think that the human vision system or you read the human vision system does, try writing an algorithm about it. Learning the basics has certainly helped, but I want everyone to feel really comfortable with this field because we'll be using it in some form. Several of the companies have been releasing these open frameworks. They certainly are releasing a lot of the results from the ImageNet problems that they solve. But no one knows what they're doing. So, well, okay, I'm sure people do, but most people probably aren't that far along. It's very much new. It's very fresh, and it's solving real-world problems.
So control systems, we've seen a lot of these problems before, like the Rotterdam floodgates are actually now allowed to be intervened by humans, because when your family lives behind the floodgates, you have kind of a perverse incentive to be very, very pessimistic in your estimation of the rising flood. And I think it really breaks down into kind of what's the risk, what's the reward, and then there's a lot of conversation right now. The real conversations in autonomous vehicles are what happens, although overall it's safer in a specific situation where you choose between one bad outcome and another bad outcome. And I think a lot of it is, kind of ethics discussion as much as it is technological capability. But actually, it's interesting. I was looking at the video of the autonomous vehicle. That's actually a talk where maybe 2 or 3 of our topics fuse together. So maybe we'll dig into that as an application spot at some point. We have one more question. I think we're going to have to cut this one off so we can kind of reload, go to the restroom and go for the next one. But this gentleman here had a question.
So I saw a blog recently that Tesla just passed 4 billion miles on their autopilot technology. I want to ask, what is your opinion in terms of how their approach with self-driving cars in terms of collecting data or with their software and hardware, even though it's kind of like a beta release essentially? It's not a full self-autonomous vehicle yet, but it does have some capabilities. What's your opinion on their approach, and what are some pros and cons on that particular platform?
Yeah, I'm certainly no expert on that, but I think I like their solution. I don't like any of the LiDAR examples because it just seems too expensive and clunky, etc. I think they have been shifting more towards computer vision approaches, relying more on that. I guess they had it after the crash. They did actually use the radar a little bit more, but so for their problem, you're looking at more like a stereo vision, or in this case, you might have like 8 cameras that are associated with it, or radar, fusing them all together. I think it's a really good way to solve the problem. I think it's cheap. It feels right. I mean, we work on mobile phones with 1 camera, but certainly understand, fusing various types of technologies. We fuse the accelerometer, the orientation sensor on the phone, or the compass with what we're seeing in video. I think Tesla does that, and I really have a lot of respect for them. I know they use deep learning. I mean, I know everyone's using classifiers. Even there was another NVIDIA demo with this exact same car where they were clearly using classifiers. I don't think there's any right approach, but I think they're probably, if I had to vote on them, I think it's probably down to them and between Tesla and NVIDIA. The Uber stuff might be having more legal problems right now than anything else, but it seems right to me. I did a little bit of robotics in college, and it's very akin to that. We were dumpster diving for parts and stuff like that. So I understand being cheap with technology. For this to succeed, we're going to need to write really good software. We're going to need to keep the cost way down. Laser technology, unless there are improvements in cost, but I think they probably have the best solution. NVIDIA though is making major progress. And who knows who wins? Maybe everyone wins. I mean, we've had competitors and they've disappeared or come about, and we're all winning. So I'm really impressed with what they've done.
I just got a whole that question since you brought up a good point about ethics. So, in terms of, I'm sorry, but just how many years do you estimate in terms of as far as where the general public are kind of adapt to the self-driving car technology in general? I mean, if you go back 10 years ago, no one would ever believe in the fact to have a computer in their pocket. But nowadays, most of us can live without smartphones. You know, in terms of along with the technology, the software, how many years do you think where the general public had a positive reception on self-driving technology as a whole?
I think, it seems like the first place it's really going to start is for truck drivers. It seems like that it has a lot more use there. I think people maybe it'll get bored. I hope not. But I think we're very close. I certainly would not have said 5 years ago that we were any less than 20 years off. But it's looking like it might be 5 years or even who knows, even 1. But I think the biggest thing that's holding everything back is probably laws. And like you said, I mean, these scenarios of pedestrians or whatever are very rare occurrences, but they make big headlines. And so until we can kind of become more comfortable that we are really saving lives with this, and already if Tesla was to turn on full autonomy, I'm sure it would reduce accident rates. They can probably prove it because they at least show what kind of decisions the car would have made. But right now, you look at Facebook, you look at even Twitter possibly, and Google and Tesla, and right now they're just gathering as much data as possible. And that's where the real money is. They said that the first trillionaire, if it's not Bill Gates, is probably going to be in artificial intelligence. And I feel like it's going to be Facebook because they just have this huge amount of data coming in and around human decision making and things like that.
So a couple points. First of all, we imagined the computer in the pocket a long time ago, tricorder, and there's lots of really good sensation on this, so I encourage everybody to take a look there. Also, Brendan Clement actually gave a really good talk on kind of data and the future of transportation in Tech Week last year, where it was a lot of the deep learning algorithms are really driven by ground truth and kind of an expert mediated foundation. And so some of the kind of things that are going to eat some part of the world are already being trained by people, right? And so to having kind of a cleaned up, refined data set that is tagged, identified makes a lot of this stuff easier. And so that's a really good talk to dig into. I want to thank Joel for the time, really good talk. Round of applause. Let's kind of fill up on snacks, drinks, whatever, run to the restroom if you need to, and we'll get started probably just under 10 minutes, just to give everybody enough time with the next talk. Thank you.
So you mentioned about C++. Yes, you like really have to
Yeah, he's talking about
Oh, you do?
okay.
I didn't mention that, but we use that.
some of the stuff
Well,
yeah. So what I know, I did especially.
So it's going to be
doing various.
Can you pass this over to us tonight? Yeah.
Is this live currently?
It is live, but it's okay.
Assembly is.
We're doing it live.
We're doing it live, Facebook or whatever.
Google. Still. How's that look? I need to move. Good. Bad. Good.
Do it in production.
The door by the parking garage?
Maybe do all this at the same time when you come to it. They are basic and
I started
Nothing much, just having a hang out, it's pretty good. I just sent you a link to your personal email. Everybody else is just invite you. All these like yeah, I sent the link unfortunately to your personal life. I sent it to the your personal one?
Okay, there we go.
I see you. Okay, no, I see you. You're good.
Hey, look at
Hey,
that.
look at that.
Magic.
Okay, we
see you.
And it's like I'm
I'm on your Google, so you hear me over here as well.
Right. Right.
I'm gonna hang up and then we'll get started
Great.
here in just a minute.
Perfect. No rush.
You look good, and that's the room. Okay, cool.
Okay, let's get settled in for the second talk. AI and natural language, or yes, machine learning and natural language, I believe is the title of the talk. So a little bit of background. Adam, can you hear us, by the way?
Yeah.
Can you, yeah, okay, good. So that was a way. I think he was figuring out how to share his screen, which is, yes. So he can see us, we got proof.
Great.
Great, we can hear you, awesome. So we figured out the Hangout thing. Imagine 2017, teleconferencing still a thing, even with good bandwidth. Adam and I go back actually quite a ways, and I want to thank him personally for jumping in to give a pretty cool talk. I have a second to flip through the slides and kind of take a look around what he's going to be talking about. It's pretty cool. Adam's working on some of the fundamental building blocks of recognition in sentences of this company Signal N, sorry, a little glitch there, in Palo Alto. So maybe he'll tell us a little bit about that, but he's going to give a talk on kind of some of the capabilities and limitations of machine learning for natural language. It's a great talk, and Adam, again, thanks for joining us, and I'll just turn it right over to you. And then we'll kind of at the end open up for some Q&A and go from there. So you're on. Thanks.
Cool. So, you see that?
Yes.
Perfect. So likewise, Ilya, great to see you again. I guess we go back almost, I don't want to say how many years, but more than 10 years at this point. More like 15. And great to be sort of virtually back in the Kansas City area. This talk is about machine intelligence for human language, which is sort of just the intersection of everything about language and everything about, computing. So here we see a problem already with language and computing. The Chinese character didn't work. I mostly work with machine translation, which of course involves multiple languages. But for most of what we're going to be talking about, it applies also to any sort of problem just in English. So many of you might have seen this. At what do we want? Natural language processing. When do we want it? Sorry, when do we want what? This is sort of a typical Alexa, Siri, machine, non-humanoid response. And we can dig into that problem later. So I guess that sort of typifies the mistakes that we're using with natural language interfaces, when we interact with machines. And yet at the same time, we have self-driving cars, we have self-driving drones, right? Self-driving flying things. But we still can't get this right. Is it really harder? So we're going to dig into that question. And I guess we can start off saying that language is intelligence, very human. There is intelligence without language, but there is not really language without intelligence, hopefully. So it's evolving also, always changing. We couldn't understand the English of 1,000 years ago. We may not be able to understand what children are saying in a high school these days. And it's self-aware, similar to other complex systems like the stock market, or it's self-aware to the point that we can sort of get very self-referential, talking about the fact that we're talking about it. At the same time, it's very simple, or deceptively simple, I would say. In the case of English and every other alphabet that's sort of descended from the Roman alphabet, you have about 26 letters. And yet you can express basically everything that you want to, right? The whole history of the world at some level. So you don't underestimate. You can do the math, right? So you can't express everything in language, as they say, there's worth 1,000 words. But you can still express ideas with language. So why is this harder than self-driving cars? There are a lot of reasons. One of the trivial ones is context. We often don't feed machines context, and then we expect them to get these problems. For example, if there is a, let's say, a new Apple release, if your data model was trained before Apple, the company, was a thing, you can't expect the machine to know that Apple, in this case, is not a fruit. So And this stuff is happening all the time. I saw a headline that said, nice truck attack. Well, that was about Nice, the city in France, and that had happened that week. So the world around us is changing. And right now, you know, a lot of these models are not retraining live, online. Now, another issue is sort of your natural robustness as a human. Can you understand this? I mean, it's really simple for us. Our brains just naturally handle this. And I don't mean to show this as the hardest thing, but we can get into much, much harder examples, but rather to show you how even something very easy can trip up machines. So let's jump into some concrete examples of natural language problems. Stuff you already use: search, autocorrect. I'm not saying it always works well, but it's there, and it's actually pain to turn it off too. Can't live with it, can't live without it. Spam and anti-spam are both sort of, right? The spammers also use some of these techniques. Voice, both voice input and the voice synthesis, which has gotten better. And sentiment, so something like automatically detecting if a review is positive or negative. And translation, transliteration. I mean, these are just some examples. There are also, under the hood, these sort of building blocks, named entities. So Apple versus Apple, the company, versus Apple, the fruit. This is a very important area because these tend to be sort of interesting things in our data. Stemming, like removing the ing from stemming, we get stem. Lemmatization, which is subtly different. Language models, just the sort of the underlying probabilities that a language a word comes after other words, for example, and syntax parsing, right? Whether given a sentence, you know, the noun, the verb, and also important things for, let's say, a chatbot: is this sentence a question or not? And then last but not least, one of the most important building blocks is just data. And everything that comes with that, including data processing, pre-processing, and so on. Now we have, we can also look at example problem types. So recognition, like image recognition, basically OCR, right? Text recognition from images, speech recognition, clustering and classification, like spam, summarization, for example, the snippets that you see in a Google search result are sort of the best sentence that most represents the page. Prediction, let's say predicting the next word, like with autocorrect or a drop-down suggestion or a search suggestion or a YouTube suggestion. Understanding would be, you know, real AI, let's say, or in a chatbot. You know, we're not quite there yet, but there are many applications. And generation, machines generate content, right? You have financial articles written based on stock movements. You have spam auto-generated. There's potentially poetry. There have been research papers that were submitted and approved that were actually just generated by bots from trained on other research papers. So then coming back to sort of the reality of machine intelligence for human language, where are we today? And I mean, it's mixed. Machine intelligence for natural language is definitely behind machine intelligence for images. And that's an interesting philosophical conversation. But, you know, real quick to back up, how most of these applications work is they take a sound or an image or text input, in which case we can skip that step, and they get it into text. And everything we do, like the clustering, the entity recognition, the syntax parsing, that's all done with text. Like when we're talking about human language, we're really talking about human text, to be honest. I mean, in practice, after that initial step. And the that speech recognition part, getting it into text, that really has been revolutionized already. I would call it solved from my perspective. There are always problems, and text recognition, I think, will also converge towards that. And the reason that we can call it solved is not because it's perfect, but because it's better than human. So Microsoft sort of tooted their horn about this with one of their results, right? So that they might have only got, I can't remember what it was, let's say 98%, but humans only got 97% on the same data set, because humans also don't recognize speech perfectly. They also make transcription mistakes. So let's consider this in the big picture sort of solved. Then on the unsolved or unsolvable side, we have something like natural language understanding, right? Where you just have a chatbot where you can arbitrarily send it, or something like CD, where you can arbitrarily send it text and have conversations with it, and it answers you intelligently. That's really far off. So the thing with those kind of inputs like Siri or Google Now is that 10 commands sort of works, right? We can remember like next song, next album, or something like this. A human can sort of memorize those commands. It becomes almost like using the command line, but just spoken. 1,000 is really too many for us to remember, but it's also too few for full coverage. And that's sort of where we are right now with these things, where you use it and it covers some things, and then you start getting into more queries, or you know, the next day something comes to your mind, and then you realize it's actually not doing anything like full coverage. And it breaks, and then you're frustrated because it sort of created this expectation that it would cover everything. Now, of course, if it does cover everything, that's great, but that's full AI, and we don't have that. There's no sort of intelligent agent, virtual assistant that takes arbitrary input and gives intelligent answers, except those which have a human working behind the scenes to handle queries that the machine can. And that's a common approach. So success really depends on how we frame the problem, and a lot of that is about UI, not AI. Just creating the expectation around what is the domain, scoping things down to the point that the users don't get frustrated, and having a sort of good recovery to say, sorry, the options are A, B, and C. You can't just say X. So where is all of this machine intelligence for natural language going? I mean, rules-based, like with the rest of AI, rules-based used to be the thing. Just an algorithm, if this to that. Back in the day, we have long moved on to statistical approaches. Translation, let's say, was rules-based back in the days of Alta Vista Babelfish in the 90s, and Systrans, and those got swapped out around in the early 2000s, definitely by 2005. So Google Translate was statistical basically from the beginning. So, and then these days in machine learning, we're of course moving towards deep learning, and that sort of means fewer parts, less of those building blocks, and more data, a lot more data. And we can sort of jump into one example of that. There's a very well-known example. So let's imagine that we sort of want to make a data model, right, which is essentially a spreadsheet, a big table that represents text like this sentence, and other sentences. And what we would end up with is a matrix that's sort of infinitely wide, right? Because we would have for every what is the count of how in this sentence? It's 1. What is the count? And that's one column. What is the count of apple in this sentence? 0, and so on and so forth. And we end up with we have to cover every word in the language, right? If we're having a data model that includes all sentences, not just this one. And so we get something that's 1 million wide, but most of the values are zeros, and that's a very sparse matrix. and very hard to compare. It's hard to compare one sentence to the other sentence and so on. And so we kind of try to do dimensionality reduction. And this is called word vectors, vectorization, right? So basically just how do we turn these letters, which we can't really work with, into numbers, which we can, right? And that's essentially what they've done with images too, is turn the images into numerical representations. So in this case, it doesn't necessarily matter. It could be that each 2 words is a unit, or that each 10 letters is a unit. But if we train, and this is actually the more famous model, because it's slightly earlier, is called Word2Vec, and this is a slightly different version called GLUB. This model represents words in the high dimensional space, but not 1,000,000 dimensions, but roughly 200 dimensions. And based on the words commonly seen around it. So for example, my brother and my sister occurs more frequently than apple brother and apple sister. And there is an interesting property of this. You notice that, so there are, again, about, let's say, 200 dimensions here. And one of these dimensions, the one shown in this graph, apparently represents gender, right? Because these words, you notice that the offset between these pairs that we might link that only differ by gender, the offset is roughly in the same direction in all of the examples. So that's sort of been isolated just from the data. No, the machine doesn't know what this line represents. It doesn't even know about these pairs, but people have found that one of these dimensions has this property. The property is not actually that useful. You can't just take from the point man. It's not precise enough that you could find the point woman based on the average of these lines, but it's still interesting, and it gives you a good idea, intuitive sense of how these models work. So similarly, we have CEOs to companies. And of course, sometimes it makes mistakes. Sometimes there are complications because, right, the company is a filiale of the other company, and or the CEO has just quit, or all kind of weird things in your data. So take this all with a grain of salt. And it even works for words that are, we wouldn't call words that are numbers. It doesn't care. These models do not care. Is it a punctuation mark? Is it a space? Is it a number? They just eat everything up. So these are zip codes, actually. So to recap, word vectors, they're imperfect, they're not predictive, and they're just a bag of words. So for example, unless you do something fancy, right, if you have 3 words like New York City, you just have to sum them or average them, because you need a single vector in order to compare to other vectors. If you have a sentence, if you have 2 sentences and you want to take the mathematical distance between them, they need to have the 2 vectors that you're comparing need to have the same amount of dimensions. So you always run into these lossy compression schemes. Now, it also needs a lot of data. Otherwise, it doesn't work. But data and machines are pretty cheap these days, which is why these models have become popular. The real advantage of these is that it's easy to train, which just lets you iterate a lot faster. You don't need a segmenter. You don't need a segmenter for example, for Somali. You don't need to worry about recognizing numbers necessarily. You don't need to worry about punctuation. It works on Chinese. It works on Thai. Thai does not have spaces between the words. They write without spaces. So, but these models are pretty robust to all of that. And when you're working on a system like in Facebook or Google, where you have to basically work on, or ideally work on 100+ languages from launch day one, that's a really big advantage. And of course, the data that you have may not be labeled by language in the first place. So some other challenges in terms of where this is all going. I mean, sometimes it's useful to have all of this happening right on a device locally without an internet connection because of reasons around surveillance, because of reasons around performance and latency. So I know somebody who works on classifying emails for corporate customers. They don't want their emails going to a cloud for that classification. It happens right there. So, and again, to stress, at this point, there are about 3.5 billion users online. The English-speaking world is sort of saturated. They're coming along online much faster in Africa, Asia, South America. And so what's happening really is that you only have about 500 million people who speak English natively and 1 billion who speak it sort of natively or non-natively, maybe 2 depending on what the level that we count. So what that means is that English is long ago became the minority language on the web. There is no majority language on the web. And as these people, you know, including myself and many people in this room, you know, come online, then the balance gets shifted. It's right at this point, again, 3.5 billion people. So 2.5 don't speak English at all. They don't, it's not that they don't speak it at home, they don't speak it at all. So, and at the same time, they're writing in the alphabets of those languages or sometimes in the Latin alphabet. So it's a big chaos, a big, beautiful mess, and there are more and more data every day. So that's kind of where this is all headed. I would say not that we've cracked it, but quite the opposite. It's just the beginning. So with that, I'll open it up to questions.
Okay, we are back. Let's see. Maybe stop sharing your screen also. Make sure you get it. And then, yeah, so super conversational. We ran just a little long on our end. So maybe 10 or 12 minutes for questions with the group. Who's got a question? John's got a question. Okay, hold on.
I'll throw a question out. Okay. Thanks a lot for sharing that with us. Something I don't have a really good intuitive feel for, I'd be really interested to know. Let's say that we had, we created a conversational AI in English that worked as well as, let's say, 30% of people, which would, or maybe we shouldn't set the bar that high. I'd say it works as well as like a 5 or 6 year old, right? Because I can talk to my 6-year-old, he understands everything. How far away are you from having a conversational AI that would work in any language? You're like, is that an enormous step because each language is so differentiated, or do you feel that the problem will be generalized enough that once we can crack it for a single language, that we might be able to crack it for all languages?
So I think that getting it to the level of the 6-year-old is very, very hard, actually. I wouldn't underestimate this. And but once it's working for English, yes, it will work for all languages. And even though, of course, there's still far more data for English than for most languages, there is still more data for smaller languages today than there was for English, let's say, in the year 2000. So, and most of the newer approaches are easier to transfer across languages. Whereas it was really the old approaches that were like job creation for guys like me.
Basic approaches, right, were all language specific, and the new approaches are generalized.
Or even machine learning based statistical approaches, but ones which had first a segmenter, which detects where the sentence boundaries are, then word separation, which also handles things like don't, which is sort of do not, and then a parser, and then named entity recognizer. And you needed all of these components, say like 12 for every single language that we launched. We're moving away from that. thankfully.
Not for sentiment yet. I don't know how much sentiment analysis you've looked at recently, but it's still a hot mess with a lot of the kind of the things that you just talked about.
Yeah, I mean, I'm not saying everybody is on the new stack yet. In fact, I would say almost nobody purely is. Even Google, which claims it, I mean, they're claiming it for some languages and not for others.
Yeah, Bag Words is still with us. Good question, John. Who else? Mike? Okay.
So language is just a tool for communication, right? But there's different tools for communication, for example, body language. So do you know if there's any research area where you're using computer vision and natural language processing to make fill in some context that might be missing if we're just looking at text?
The audio is.
Can you hear this better?
Yeah.
Adam?
I can hear you better.
Okay, so I'll repeat the question. Communications is only maybe 5-7% written language, the words that you use. What have you seen as far as facial expression, body posture, tonality, kind of the filling in the rest of the gaps in full human communications?
You're very right about that. I'm probably the wrong guy to ask, in the sense that I only deal with text. But these models actually work well with that in the sense that you could have a bunch of columns, and one of the columns is also a vector representing the image of the person's face. So you have some vector representing the text and another one representing the face, and then the output label, and it really will just sort of eat it all up. But what I have seen, and this is a really sort of one of those things where you think, why didn't I think of that? What they've done is taken YouTube transcripts or other video transcripts and then removed the audio, and then the text is the output. It's shown the text in the training, but not in the live test, and use basically the lip movements to predict the test, to predict the text. So really only by deleting the audio, they were able to create this awesome data set to teach machines to understand better with the help of the images. And it's very possible the machines, when they're taking in image vectors, it may not be looking at the lips. It may be looking at the guy's shoulders. The shoulders are what statistically indicated that the word to write was no, not yet. So, and I can follow up with a link to Ilya about that project. But, definitely, that would be something in the direction that you're talking about.
Cool, yeah, I'll be interested in seeing that.
And I will put that on the meetup group, so hopefully everybody that's seen the meetup group joined it, because then we can kind of continue that conversation there, and then I can get on beer next time. Okay, other question. I can also, by the way, fill in the gaps on some of that, because my previous company was facial expression, body posture for reaction, and it's actually interesting. I have some facets that you can add to your model, and that could be pretty interesting. So we'll take that conversation offline. All right, other questions from the audience? Oh, let me get a microphone too. Here we go.
Hi. How does this word vector model differ from LSA, like semantic analysis?
Did you hear that, Adam?
Yes, yes, I did. Or rather, yes. So how do these new word vec models differ from latent semantic analysis? I think that's a good question. I think it's fair to say that conceptually they're very similar. They're just being it's sort of LSA on steroids. But you're right. For those who have been paying attention, a lot of these concepts sort of get recycled every generation or half generation. but we have better computing power now, more data now, and and the other thing that's happening is that people are releasing things, and it's really hard to check, what has been launched before. There is some sort of pressure to come up with a new name. Some people are complaining that people don't read the old papers before claiming that they found a new result. So, I mean, not to knock word vectors at all. It's really powerful technique, but I think it's conceptually similar, but word vectors is really trimmed down and really optimal for feeding to today's neural networks, basically.
Awesome. Maybe one more question. Any last second questions? Okay, I have a bunch of questions I can ask, but in interest of wrapping this up, I try to keep everybody under 2 hours and really under less than an hour and a half, actually less than seats. And so we're right on the kind of margin there. So I think let's give Adam a round of applause and a special kind of filled in the breach and gave a really interesting talk on like no notice at all. That's awesome. I will follow up with you to get kind of the link. Maybe we can even talk into getting added to the meetup groups so you know we're up to. And it's great to see you and see that you're still doing well after more than a decade. And thanks for revealing that to the group. I thought that's awesome.
Likewise.
All right. Well, thanks for joining us and cool. Thanks. Thank you. All right, so for kind of the folks in the building, to get John out of here since he's been super patient and a great host. Okay, maybe we can kind of pick up, make sure that we kind of throw things away. Generally, hold on 2 seconds. Who's on the meetup group? Who knows where to find the meetup group? So if you need to find the meetup group, the number one, billionbits.com, and then most of the. Actually, you know what? If you just Google 1 billion bits meetup, you'll find us. But if you can join that, then we can kind of estimate who's coming. And also, it's a really good way to stay in touch. And I'll toss up some of the links, content. This video will be up there. And it seems like we can get kind of a decent turnout and ideas for topics, things like that. We can do these really as often as as they're interesting. So let's keep that conversation going. Thanks for coming out. This was a really good turnout, good questions, good conversation. I can fill in the holes on some of the semantic stuff for you, Mike. Generally, send questions to the meetup, or you can, if you Google Iliad Kansas City, you pretty much find me. So it's not so hard to get in touch with me. If anybody wants to organize a meeting or anything like that, I'd love to hear about it. Yeah, so we can pick up and kind of mill around for a little bit, and then we'll try to kind of close this thing down relatively quickly. Well, thanks a lot for coming. I appreciate it, guys. And thanks for everybody's participation and help.